An interstellar object is passing through our solar system right now, and scientists are racing to capture detailed observations before it leaves forever. The third confirmed visitor from beyond our cosmic neighborhood, 3I Atlas, has generated both scientific interest and public speculation. As new data arrives, we're learning what this object actually is, and what it can teach us about planetary systems beyond our own. As always, if you're interested in the latest space discoveries, leave a comment and subscribe to stay up to date with all the news as it's released. Let's get into it. As of mid-November 2025, 3I Atlas continues its journey through the inner solar system, with ongoing observations from multiple facilities worldwide. The object is scheduled to make its closest approach to Earth on December 19, 2025, passing at a safe distance of approximately 170 million miles, roughly the distance between Earth and the Sun. This presents an excellent opportunity for detailed spectroscopic and imaging studies, using both the James Webb Space Telescope and Hubble Space Telescope. Astronomers expect these observations to provide comprehensive data on the object's composition, structure, and activity patterns. Spectroscopic analysis will identify specific molecules being released, helping determine what volatile materials the comet contains and how they compare to both solar system comets and 2I Borisov, the previous well-studied interstellar visitor. High-resolution imaging may reveal details of the nucleus structure, active regions, and dust grain properties that are invisible in current observations. The scientific goals are straightforward. Characterize this interstellar visitor as thoroughly as possible to understand its origins and how it compares to objects in our own solar system. Every interstellar object provides a sample of material from another planetary system, offering insights into star and planet formation processes beyond our Sun. Whether 3I Atlas proves similar to or different from solar system comets, the data will advance understanding of how planetary systems evolve and what happens to material ejected during their formation. Researchers are approaching the December observations with standard scientific methodology. The working hypothesis, supported by all current data, is that 3I Atlas is a natural comet containing frozen volatiles and rocky or metallic grains formed in the outer regions of another star system. The upcoming observations will help confirm this understanding and provide detailed characterization of its properties for comparison with other known interstellar and solar system objects. On October 29, 2025, 3I Atlas reached perihelion, its closest approach to the Sun. As expected for a comet approaching peak solar heating, the object's activity increased noticeably during this period. Observations from observatories in Chile and South Africa captured the development of a more prominent dust tail extending away from the Sun, a characteristic feature of standard cometary behavior when volatile ices sublimate under intense solar radiation. The tail formation occurred over several days as solar radiation heated the surface and subsurface materials, causing increased sublimation of volatile ices. This process released both gas and dust particles, which were then pushed away from the Sun by solar radiation pressure and the solar wind. The rate of tail development was brisk, but fell within observed rates for comets undergoing rapid heating near perihelion, consistent with natural processes. Some observations suggested possible multiple active regions on the nucleus, indicated by subtle structures in the developing tail. Multiple active areas are common in comets, as different parts of the surface may have varying compositions or orientations relative to the Sun. Jets emanating from specific vents or fractures can create complex patterns in the surrounding coma and tail. These features provide valuable information about the internal structure and composition of the comet nucleus. There were no confirmed reports of unusual fragmentation or unexpected changes that would indicate anything beyond normal cometary activity. While comets can fragment near perihelion due to thermal stress from rapid heating, 3I Atlas appeared to remain intact as a single body through this critical phase, allowing for continued observation as it moved away from its closest solar approach. Questions arose in early November regarding the timing of high-resolution image releases from certain observatories. Images captured in early October weren't immediately made public, which led to some speculation about potential delays. However, NASA officials explained that the timeline reflected standard procedures involving data processing, analysis by research teams, and coordination with university partners who contribute to instrument development and operation. The delay wasn't unusual for astronomical observations of this type. Research teams typically have proprietary periods to analyze data before public release, particularly when instruments involve partnerships between government agencies and academic institutions. The processing of high-resolution astronomical images also requires careful calibration and validation to ensure accuracy before distribution to the broader scientific community and public. While the pace of release may have seemed slow to public observers eager for new information, it followed established scientific protocols used across the field. The comparison some made to other NASA image releases isn't entirely applicable, as different missions and instruments operate under different data policies. Mars rover images, for instance, come from NASA-operated missions with different guidelines than Earth-based telescope observations involving multiple institutional partners. The situation didn't indicate anything unusual about 3I Atlas itself, but rather reflected the normal complexities of collaborative astronomical research, where multiple institutions and research teams coordinate their efforts and share responsibilities for data validation and publication. In July 2025, NASA's Atlas telescope system in Chile detected an object moving through space on a trajectory that indicated an origin beyond our solar system. Within days of its discovery, researchers confirmed what they suspected. This was the third known interstellar visitor to pass through our cosmic neighborhood, following Oumuamua in 2017 and 2I Borisov in 2019. The object represented another valuable opportunity to study material from other star systems. Early estimates suggested the object stretched roughly 3.5 miles across, placing it in the size range of a small comet or asteroid. Its velocity, approximately 137,000 miles per hour relative to the Sun, clearly marked it as an interstellar traveler rather than a solar system native. Initial orbital calculations showed it approaching from beyond Neptune's orbit at an angle suggesting an origin from the general direction of the constellation Hercules. Astronomers immediately began coordinating observation campaigns across multiple continents, knowing that opportunities to study interstellar objects are exceptionally rare. What made the discovery particularly significant was its timing. Detection capabilities have improved substantially since Oumuamua's appearance 8 years earlier. The Atlas system, designed to scan for near-Earth objects, had been upgraded with more sensitive detectors and faster processing algorithms. This meant 3I Atlas was caught earlier in its approach than previous interstellar visitors, giving scientists months rather than weeks to plan detailed observations. To understand the context around 3I Atlas, it's important to know about Oumuamua. In 2017, that object became the first confirmed interstellar visitor ever detected. It displayed unusual characteristics, including an elongated shape suggested by light curve variations and a small acceleration that couldn't initially be explained by standard outgassing models. The acceleration was notable because Oumuamua showed no clear visible signs of the gas jets that typically cause such motion in comets. Dr. Avi Loeb, then chair of Harvard's astronomy department, proposed that Oumuamua's acceleration could be explained by solar radiation pressure acting on a thin surface. He raised the hypothesis that it might be artificial in origin, possibly a light sail from another civilization. Most astronomers disagreed with this interpretation, instead proposing various natural mechanisms including sublimation of exotic ices like frozen hydrogen or nitrogen that wouldn't produce visible jets. Multiple peer-reviewed papers offered alternative explanations for Oumuamua's behavior within the framework of natural phenomena. In 2019, 2I Borisov arrived and displayed clear cometary behavior with a visible tail and detectable gas emissions. Spectroscopic analysis confirmed it contained water vapor, carbon monoxide, and other molecules typical of solar system comets. Its composition and behavior closely resembled objects from our own outer solar system, supporting the view that most interstellar objects are likely to be ordinary comets and asteroids ejected from other planetary systems during their formation. For many researchers, Borisov represented the expected norm for interstellar visitors, while Oumuamua remained an outlier that might be explained by unusual but natural composition or structure. When 3I Atlas was discovered, some early observations led to comparisons with Oumuamua, though as data accumulated throughout the fall of 2025, the scientific picture became clearer. In mid-October 2025, Dr. Loeb circulated preliminary analysis, suggesting that 3I Atlas might exhibit unusual characteristics worth investigating further. According to his early interpretations, certain orbital features appeared statistically unlikely for a randomly arriving interstellar object. He raised questions about the object's trajectory and its passage through the inner solar system, suggesting these warranted closer examination beyond standard observational protocols. Loeb's initial claims included observations about the object's orbital alignment and its path relative to the major planets. He suggested the trajectory showed what he characterized as remarkable precision in its approach, proposing this might indicate something beyond random chance. These early interpretations generated significant media attention and public interest, with discussions appearing on popular podcasts and social media platforms throughout October. However, it's important to note that these were preliminary interpretations based on early data, not peer-reviewed conclusions accepted by the broader scientific community. The astronomical community's response was measured. While acknowledging that 3i Atlas presented interesting observational opportunities, as any interstellar object would, most researchers emphasized the need for careful data collection and thorough analysis before drawing conclusions about unusual behavior. Several astronomers pointed out that initial orbital determinations for distant objects often require refinement as more observations accumulate over time. What appears unusual with limited data may prove entirely consistent with natural behavior once the full dataset is analyzed and models are refined with better parameters. As observations of 3i Atlas continued through October and early November, researchers gathered more comprehensive data about its characteristics. Some of the early claims that generated initial excitement required reevaluation in light of better information and refined orbital calculations. The trajectory that initially seemed to show unusual alignment turned out to be consistent with objects arriving from interstellar space at various angles and velocities. While any specific trajectory has low individual probability when calculated in isolation, the range of possible trajectories for interstellar objects is vast. 3i Atlas fell well within expected parameters when considered as part of this broader population. The object's position relative to the Sun during perihelion, which some early interpretations suggested could limit observations, is actually a common occurrence for comets and asteroids on certain orbital paths, dictated by where they enter the solar system. Astronomers routinely work around such geometries using space-based observatories and by coordinating observations from multiple ground-based locations at different longitudes. The timing presented observational challenges but not insurmountable ones, and certainly not evidence of anything beyond natural orbital mechanics governed by gravity and momentum. Regarding acceleration, initial reports noted changes in the object's velocity that weren't immediately accounted for in preliminary models. As more detailed observations became available throughout October, these changes appeared consistent with outgassing activity typical of comets as they approach the Sun and volatile materials begin to sublimate. Cometary acceleration occurs when these volatiles create jets that act as natural thrusters, and the observed accelerations fell within the range expected for active cometary bodies. Spectroscopic observations of 3i Atlas throughout the fall detected various elements and compounds being released from the object as it heated up. Early reports mentioned nickel detection, which generated some speculation because nickel is also found in metallic alloys used in industrial applications. However, nickel is actually a common component of many asteroids and meteorites, particularly iron-nickel meteorites, that form in the cores of differentiated bodies in planetary systems. Finding nickel in cometary material is less common than in asteroids, but not unprecedented. It can occur when a comet contains rocky or metallic grains mixed with ice, which may provide information about conditions and processes in its parent star system. The presence of nickel doesn't indicate artificial construction, according to mainstream scientific interpretation. Rather, it suggests 3i Atlas may have a composition that includes metal-rich components alongside volatile ices. As 3i Atlas moved closer to the Sun, it did develop a visible coma and tail, though the initial activity was relatively subdued compared to some solar system comets of similar size. This variation in activity levels is well documented among comets and depends on factors like surface composition, thermal history, and the distribution of volatile materials within the nucleus. Some comets are highly active with prominent tails, while others show minimal outgassing even at close solar distances. The activity level of 3i Atlas appeared to fall within the observed range for comets, though at the lower end initially. The gas-to-dust ratio observation suggested the object was releasing significant dust relative to gas, which could indicate either a composition with less volatile ice than typical comets, or a surface structure that preferentially releases dust particles. Both scenarios are observed in various solar system comets and don't require exotic explanations beyond standard cometary science. The story of 3i Atlas shows how scientific understanding develops through observation. Early interpretations sometimes suggest unusual characteristics that prove consistent with natural phenomena once more data arrives. As the third confirmed interstellar object studied in detail, 3i Atlas provides valuable data about material from beyond our solar system. The December observations should deliver the most detailed information yet for an interstellar comet, resolving questions about its composition and behavior. If this breakdown of the science behind 3i Atlas was helpful, subscribe to stay updated when the December observation results are released. Drop a comment below with your questions about interstellar objects or what aspects of space science you'd like to see covered next. Thanks for watching, and see you in the next video.